Good morning. In this presentation we will see the functioning of the ASA Pro Cable Trays module, which allows the 3D modelling of electrical raceways and conduits, and the ASA Pro Cable Routing module that allows the routing of cables into the previously modelled cable trays. ASA Pro Cable Trays is a simple AutoCAD application, so beside the standard AutoCAD interface we have a customized menu which contains the application commands. Now let's go open an example. The sample file we'll use for this presentation is actually made up of two parts. There is the first part that contains the electrical cabinets and supports, and another part that is just an external reference. Thus, a DWG file that has been attached to the current drawing as an XREF. In fact, if we select the file, we see that the original DWG is 15 megabytes. When you're working on tricky models, there may be a need to simplify visualizations. In AutoCAD, there is a possibility to clip an external reference. Clipping an external reference helps you to focus the working area. Then we create a rectangular clipping box, which starts from the left and comes exactly under the grating. In this way, we're going to exclude all the objects outside this volume. Now we're ready to get started. Before starting modelling, let's see the catalogue of commercial parts supplied with the ASA Pro. Launch Data Management and click on Cable Trays. Here we have a set of manufacturers, each of which contains the dimensional catalogues for different products, such as Legrand. Let's take, for example, Femi height 50 millimeters. Here we have the straight elements and the 60 degrees, 45 degrees and 90 degrees elbows. By clicking on Modify, we open the dimensional parameters of straight elements. Here we have the different widths and the height, which in this case is obviously 50 millimeters. Here we have the thickness and the corresponding part number of the straight element, the weight of the cover with part number and corresponding description. And here we have the cover lock pairs per linear meter with part number and relative description. The same approach is followed for the elbows. Here we have the part number for the elbows, the covers and the cover locks. On the other hand, the red rows show the objects that are not available in the Femi catalogue for this particular product line. Besides the graphic objects, there are non-graphic objects that are the joints, which are counted anyway even if they are not represented graphically. The same applies to conduits. Also here we have the several manufacturers with their models, and for each of them we have the pipes with their outside diameters, junction boxes, elbows, T's and many others. The ASA Pro catalogue is fully customizable, so you can enter a new manufacturer or a cable tray model at any time. For example, we add the ZA cables manufacturer. And within this manufacturer, we are adding a new product. ZA Model 1. We also type a height, 50 millimeters. Choose a material, stainless steel in this case. And here we specify if the elements are always supplied with covers or if they are optional. We select the straight elements and add dimensions. The width is 100 millimeters and the height is 50 millimeters. Type a thickness. It's clearly possible to specify also the weight, the part number and so on. We can also add another dimension, in this case 150 by 50 millimeters. This data will clearly need to be entered for all catalogue components. Another possibility is to copy within this manufacturer a product that already exists in another catalogue. In this case, we are copying the Famy height 75mm cable trays and paste them into ZA cables. We therefore have the same dimensional data as those in the Famy catalogue that we can eventually adjust by correcting the dimensional part or simply changing the description. This is a very time-saving process. Change the material. OK. We open the straight elements and we still find the Famy's data that, if necessary, we can modify. We're ready to start modelling. We'll model our plant by connecting the main panel to a series of sub-panels. Here we have a secondary panel in another room, and to go from one room to another we will pass close to a staircase. A little further on we have a middle panel and a secondary branch that takes us to a pump's power supply panel. Here we have pump P1 and pump P2 with relative terminal blocks. Further down we have one last electrical panel that will complete our system. To help us during the modelling, we will use the reference icons. These icons are used to mark the starting or ending points of our trays. We place an icon above the main panel and another one on top of the secondary panel. Another icon will come in handy to specify a point that will be used as a reference for the raceway that will have to go from one room to another. So we're getting closer. And take a reference point on the support, midpoint. We give a distance, type 130mm, and we're going to raise 25mm. This position will become the axis elevation of our cable trays. OK. Let's continue adding the other icons. We insert an icon above the middle panel. Another above the pumps panel. And we're going to insert icons that are used to enter inside the terminal blocks. In this case, we set up a side entry. These symbols are actually AutoCAD standard blocks, so they can be copied with the normal copy command. One last reference about the terminal panel is missing and we're done. OK, our plant is ready and we can model the cable trays. But before doing this, we can also unload the 3D model. In fact, we don't need to see the graphics since we have the reference icons. We can thus lighten the whole of our work. With a simple axis, we sketch the path of our electrical raceways. We choose Famy 3, height equals 50, size 150 by 50mm. This will be the main line that connects the main panel to the terminal panel. We give a starting point, and through the plane option, we catch the elevation of the cable tray axis. With the reference icons, it's very easy to draw in 3D because it's not necessary to calculate any distance or elevation. Let's go now and draw the branch. This time we reduce the section and select 100 by 50mm. P-snap is ESAPRO's OSNAP that catches the reference icon node. The magenta plane brings us to the right elevation. Then we go against the red plane and end with perpendicular or snap. The first branch has been drawn. Here we have an intermediate branch, 150 by 50 millimeters, from P-snap to perpendicular. Let's go now to model the branch that leads to the pumps panel. Select a size, 100 by 50 millimeters, P-snap. We provide an elevation by selecting the magenta plane and ending on the perpendicular point. Now let's draw the conduits that will connect the pump's terminal blocks to the secondary branch. To do this, we take a reference point on the secondary branch and give a distance, type of value of 1250 millimeters. Now we are ready and launch the conduit axis command. We choose the manufacturer and diameter. From P-snap point to the red plane. We go down to the magenta plane and then we connect to the blue plane. Once pump P2 is connected, we move on to pump 1. Conduit axis, we choose the same size, P-snap, and we go to the blue plane and end with perpendicular. Once the axes have been drawn, the reference icons are no longer needed, so we can delete them with the AutoCAD Erase command or with the delete option of the same command we used to add them. Now we switch our UCS back to World and go to dress the naked axes. Let's launch the automatic dressing command. Select an axis to be dressed, choose the section orientation, and select the opening side for the cover. The line is automatically dressed with standard commercial length pieces. In this case, the single pieces are 3 meters long. If we go to the end of our line, we see that this straight element is 3 meters long, while the next piece will be a bit shorter, in this case 2.2 meters. Between one piece and another, joints are calculated, which are non-graphical objects, but are still counted in the bill of materials. Now let's go dress the branch that leads to the secondary panel. This time we won't draw covers, so we disable the Insert Cover option. Selecting a starting point, give a direction to our section, and the cable tray is drawn. If we go to examine the joint, we can see that we have a sharp edge. So we decide to add a junction component. We choose a reduced T from the catalogue. ASAPRO shows a message which says that the reduced T is not available in the catalogue, so we're going to replace it with a connected junction. With the same procedure, we dress the branch that leads to the motor panel. Starting point, direction, and connected junction. We add one last straight element to connect the middle panel. Straight element, starting point, ending point, direction. At this point, the cable trays part is complete. Let's go to draw our conduits. Then we select the command Automatic Dressing and dress our conduit axes. 1 and 2. To complete the conduit lines, we add a junction box at the intersection. Another way to model the cable trays is to add the pieces one by one. In this case, we start from a straight element, choose the model, the dimensions, the size is 100 by 50 millimeters. We start from an existing element and give a length, 1000 millimeters. Let's directly draw the straight element. And at this point, we're going to add an elbow. With the fit mode, we can attach another object to the pre-existing one, and it will be mounted, keeping the cover direction. Let's add up another elbow. This technique is particularly useful in tight spaces where it's not possible to calculate the path using only the axes. We attach the two elbows and then we're going to create a branch by inserting a T. It's an equal T, so it has the same inlet and outlet sizes. We give a direction. And let's add an eccentric reducer at the end, because at this point the cables will obviously split to one side or another. We continue the cable trays modeling by drawing some axes. So the two design techniques can absolutely be mixed. Where it is more convenient, you can add single pieces, and where it's easier to draw the axes, you can use the axes command. In this case, we are seeing that the axis dressing is done step by step. We insert the elbow, and we have completed the modeling of all our cable trays. Now it's time to check the general assembly. Then we go in the external references palette and reload the 3D model in memory. So we have a complete view of the plant, and we also have the ability to check the interferences. In fact, through the command drawing check, Acer Pro is able to detect all the clashes between the cable trays we've just modeled and any 3D geometries made out of solids. Now let's launch the data extraction command. With this command, we're going to save into the project database all the materials we've just added to our drawing. All materials are counted, not only cable trays but also support materials. Once the data have been extracted, we go to Data Management and launch Materials List. We choose the drawing, and an Excel sheet is generated with the list of all the materials we've modeled. We see 34 meters of 150 by 50 straight elements and 50 meters of 100 by 50 straight elements. And these are the covers. Of course, tees, cover, locks, and all related materials are counted. Let's go count the conduits. This is the bill of materials. Okay. Once the BOM is created, we are ready to create the 2D views. Go to the AutoCAD layout environment and launch the Create Views command. With this command, we create a set of predefined views, in this case a plan view scale 1 to 50. The entire model is displayed, and now we're going to clip the area to be shown. Let's place the view inside my title block. And let's add another view. This time we create an orthogonal view as a flip of the view we just generated. Click a point on the edge of the window to be projected, and generate a 90-degree flip view. We arrange the edges, and with the Draw Profiles command, we create a flat drawing that follows our 3D model with 2D entities. Launch the view calculation. This process may take time. It clearly depends on the model complexity and on the file size. The first view was projected, and this is the second view. Projection completed. The projection just created is actually a 2D AutoCAD drawing. Then we can go to dimension it with standard dimensioning commands. In this case, we're going to dimension the distance between the different supports. First, second, and third support. In addition to the linear dimensions, there are also altimetrical dimensions. For example, with this command we can show the elevation of our cable tray. By selecting the base option, we show the bottom of the straight segment. In this case, my cable trays run at a height of 2,300 millimeters. I can highlight other elevation points that may be relevant for my project. Another option is to add a set of annotations. In this case, we enable an annotation showing the dimensions of our trays. Width by height for rectangular sections or diameter for conduits. We choose the type of label, in this case it's a simple leader with text, and select the section we want to label. This makes it very easy to give information on the sizing of electrical raceways. This concludes the part of the presentation dedicated to AZA Pro cable trays. We saw then how to insert a three-dimensional model and go to model 3D cable trays in it. In this part of the video, we will see the functioning of the AZA Pro cable routing module that will allow us to do the routing of some cables inside the trays we just modeled with the AZA Pro cable trays module. Cable routing is really only based on the axes. So to make our drawing lighter, we can unload the external reference and freeze the layer that contains the 3D cable trays. We will then have a much cleaner context on which cable paths can be designed. Let's take a look at the data needed to be able to perform the routing. It starts with a listing of users. The utilities represent the cable starting and ending points. Each user will have a name, an area, and a description. Another table that is very important is the cables list. These are the cables that we're going to route, so each cable has its name, a composition, a voltage level, a start and an end. Users and cables can be manually loaded or imported from an Excel file. The Import from Spark button imports an Excel file from the electrical design software Spark Automation. Here we have a set of sheets which show the users with related information, and here we have the cable sheet. Each cable has its own name and a composition which refers to sections. And here we have the voltage level. With this field we identify the purpose of this cable. H equals high voltage, L equals low voltage, etc. Here we have the possibility to specify the from and to the start and end users. Here we have an estimated length. White fields are not mandatory. Here we have the measured length that eventually can be inserted after having physically positioned the cable. And here we have a field that allows you to bind a maximum length. This will be the maximum length that the software must not exceed when it calculates the routing. In this case, the cable must not be longer than 40 meters to not exceed the voltage drop range. Here we have an additional length for the cable. In fact, the cable has an extra length at the start and at the end in order to consider the physical connection to the terminal block. And here we have a markup percentage that can be used to correct the bill of materials. In the last column, we have a real cable identifier. In fact, you can decide how many and which cables should be in the same reel. This way, ESA Pro will not only calculate the total cable requirement, but also give the coils composition. This is very important because it gives you the option of pre-ordering coils for each cable. The last sheet contains a table of commercial cables. In the first column we have the commercial name, here we have the dimensions, then the outer diameter, the composition. But most importantly, in column E we have the section area, in practice the square millimeters that the cable takes up inside the cable tray. Here we have the additional fields, weight per meter and minimum bending radius. By specifying this last field, it's possible to constrain the software so that the cable is not overbent. In the last column, we have a description with the function of the cable. In the table levels, we have the voltage levels that we can assign to our cables, so that they are compatible with the cross-cable trays. And especially the section types table. Here we have a set of rules that define how our cable tray sections must be used. If, for example, we take a 100 by 50 mm single section, we see that the dimensions are these. 5,000 square millimeters is the overall area. And we have an 80% maximum allowable fill percentage. If we add a divider, we can decide not to use all the 5,000 millimeters for a single section, but to specify that only 3,000 are for section 1, while the other 2,000 are used for section 2, into which I can route other cables, different voltage level. The software handles up to 4 different sections. Once the configuration is complete, we return to the model and define the positions of the utilities. With Insert Utilities, we indicate the position of the first utility, which is the general panel QG01. We change the visualization style so we can see the name. And that's the second user. Let's go pick the area. This shrinks my list view. OK. And this is the QS01 subpanel. These blocks can be stretched so that multiple users can be connected to a single axis. In the case of a series of panels, here we're going to insert the motors panel. We see that the list gets shorter as we go to add the users. So going forward, fewer and fewer users are shown. Let's go to add the 2 pumps. This is the P1 pump and the second terminal block, that of the pump P2. There are still 2 users left. The middle one, QS2, and the most distant one, QS3. Obviously, if I don't insert a utility, I won't be able to route the cables that are connected to it. We've finished the user's placement and are now going to define the sections. Let's launch Sections Management. By clicking on Automatic Sections, the program recognizes all the cable tray's sections, and to each of them assigns a default name, a section type that can be changed. The section types refer to the table we've seen previously, and finally a voltage level that establishes the consistency between the section and its cable. With Find Section, it's possible to highlight a section in the drawing that we've already selected. Now let's rename the main backbone. Therefore, the section T13 becomes D1. and also rename the second piece of backbone, which will become section D2. OK. Save the configuration with the extract, sections and users command. We're now ready to route the cables. Let's launch the route cable command. We choose automatic routing. Here we have the list of cables that you can route, and I can shrink this list by applying a filter. In this we select the cables of greater area. Below we can decide if we want to see the log information or to highlight the cable's path as they are routed. This is the first path, and here is the second path. The software finds the route automatically according to the rules we've set. And here is the routing log for the first cables. By clicking on cables per section, it's possible to check the percentage of filling. In this case, the backbone is only at 29%. While Find Cables allows you to select a cable among those routed and highlight its path. The cables can also be routed manually by selecting which sections to go through. Now we're going to route a cable from the general panel to the motors panel. We'll route it manually because maybe it's a redundancy cable, and therefore it doesn't necessarily have to follow the shortest path. The possible alternatives are highlighted. Let's confirm. Users reached. We have completed the routing. Another possibility is to use a cable already routed as a pilot cable and copy its routing to another cable, which obviously has to take the same path. Here we select the cable 40 and give the same routing to the cable 50. This is clearly a very time-saving operation. Let's see how the software behaves when it detects an overfilled section. And let's select a range of cables from cable 20 to cable 94, and we automatically route them. Some of them will pass into conduits that are intentionally undersized. Let's inspect this section. And we see that the fill percentage is more than 80%. We're going to select other cables that will need to pass through this section. In fact, the 95 cables are cables that we created specifically to completely fill this section. In the first case, we have a remaining area of minus 17 square millimeters, so we could still force the route. While for the other cables, the forcing is clearly not possible, so we can look for alternative paths or quit the routing. The new fill percentage is 105.9%. Once the routing is complete, we generate the reports. Lists. Cables routing. The first report we are going to create is the cables list. This Excel sheet lists the routed cables. The cable details are what we've already entered. The most important column is the calculated length. So this is the length of the sections that the cable went through plus the extra length we set before. The second report is cables type. With this report, we can calculate the cable requirements. So we have a total length of cables to be purchased and their division into reels. In this case, the total is 147 meters, but we've split the cable in 3 reels, and these are the single lengths. Cables and sections is the actual routing report, is the one we then provide to the installer. Here each cable is shown with a list of the crossed sections. In the last columns we find the total routing length and the reference to its reel, so we actually have everything. In section and cables, we have a list of sections with all the cables that go through them. Let's apply a filter and check the cables that run on the D001 backbone. These are the cables that run inside this section. And this the filling percentage. In the right column we have the total weight of the filled section. We didn't have the weight per meter of the cable type, so it is the weight of the straight segment only. And finally, cables progress. With this report we can see the current situation. Then how many cables do we have in total? How many of them are already routed and how many more are still to route, with the progress percentage. Now let's go complete our 2D drawing with the information we got from the routing. First, we're going to add a label that shows the section name. This gives the possibility to identify within the drawing the positioning of the sections we've listed in the reports. The name of the section, its size and elevation are shown. Another very useful label is one that lists the cables that pass inside a section. Section and routed cables allows you to generate a label, text only or with a box, where the name of the section and all the cables passing through it are shown. This graphic information is immediately usable by the installer. At this point the work is done and we may return back to our model. This completes the overview of the Module and ESA Pro cable routing.